So what's a superpixel? Let's consider how we represent images. Images are represented as a grid of pixels in either single or multiple channels. We take these M cross N pixel grids and then apply algorithms to them, such as face detection and recognition, template matching, and even deep learning applied directly to the raw pixel intensity. The problem is that our pixel grid is by no means a natural representation of an image. For example, let's consider the image below. If I were to take a single pixel from the image and then show it to you on the right, could you reasonably tell me that that pixel came from the sun and that single pixel actually holds some sort of semantic meaning? The answer is a resounding no. A single pixel standing alone by itself is not a natural representation of an image. So we locally group pixels so that it could make more sense to explore and not only perceptual but semantic meanings of an image. When we perform this type of local grouping of pixels on a pixel grid, we arrive at what is called superpixels. These superpixels carry more perceptual and semantic meaning than their simple pixel grid counterparts. So now we will talk about the SLIC algorithm. SLIC stands for Simple Linear Iterative Clustering. This algorithm simply performs k-means in the 5D space of color information and image location. As the clustering method is simpler, it is very efficient. It is essential for this algorithm to work in the lab color space to obtain good results. This algorithm quickly gained momentum and is now widely used. Okay, now let's get to the coding. So we import the packages we will be using for this example. To perform the SLIC superpixel segmentation, we will be using the scikit image implementation, which we import on line 2. To draw the actual superpixel segmentations, scikit image provides us with a mark boundaries function which we import on line 3. From there, we import a utility function, img underscore s underscore float on line 4, which, as the name suggests, converts an image from an unsigned 8-bit integer to floating point data with all pixel values called to the range 0 to 1. On the following line, we import the IO subpackage of scikit image, which is used for loading and saving images. We also make use of matplotlib to plot our results, and then we load this image and convert it from an unsigned 8-bit integer to a floating point data type. So now the interesting stuff happens. We perform the SLIC superpixel segmentation on the following line. The SLIC function takes only a single required parameter, which is the image we want to perform superpixel segmentation on. However, the SLIC function also provides many optional parameters. The first is the n segments argument, which defines how many superpixel segments we want to generate. This value defaults to 100 segments. We then apply sigma, which is the smoothing Gaussian kernel applied prior to segmentation. Other optional parameters can be utilized in the function, such as the max iter, which is the maximum number of iterations for k-means, compactness, which balances the color space proximity with image space proximity, and convert to lab, which determines whether the input image should be converted to the lab color space prior to performing superpixels. Okay, so now that we have our segments, we display them using the matplotlib in the following lines. So in order to draw the segmentations, we make use of the mark boundaries function, which simply takes our original image and overlays our superpixel segmentations. Finally, our results are displayed below. And that's pretty much it. Thank you.